Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hammond, and we're going to cover exact form differential equations. So an exact differential equation is of the form m of x comma y dx plus n of x comma y dy is equal to 0, where it has this special property where the derivative of the coefficient function in front of dx with respect to y is equal to the derivative of the coefficient function in front of dy with respect to x. So really, the derivative of this with respect to this thing's variable, the dy, is equal to the derivative of this second n with respect to this one's differential dx. So if this happens and we consider this to be of exact form, and furthermore, if it's of exact form, we can really say that it has an antiderivative that has this property. So there exists this function f of x comma y equals c, where the coefficient function is the derivative of, really, we can kind of think of this as an antiderivative. Uh, so it's the derivative of our solution function with respect to x, and then n is going to be the derivative of our solution function with respect to y. So the first example, I just want to show exact, and then we'll use this in the second example with the same equation to find this solution. Okay. So first, let's example. Let's verify the differential equation is exact. So we have is 6x squared y plus y squared dx is equal to, sorry, not equal, plus 2x cubed plus 2xy dy is equal to 0. So in order to show that this thing is exact, I have to look at its coefficient function. So, this is going to be the coefficient in front of dx. That's going to be the m function. And then this function here, which is the coefficient function in front of the differential of y, which is going to be our n function. So I have to show the derivative of this thing with respect to, this differential is equal to the derivative of, the n function with respect to this differential. So we're going to show that the derivative with respect to y is going to be equal to the derivative with respect to x, and, this one with respect to y, this one with respect to x. So we have 6x squared plus x squared y plus y squared. And then over here, we have the blue function, which is going to be 2x cubed plus 2xy. Now, taking these partial derivatives, the derivative of this with respect to y is going to be equal to 6x squared, and plus the derivative of this with respect to y is 2y. And then on the other side, I have to take the derivative of this with respect to x. So the derivative of this term with respect to x is a 6x squared, and the derivative of this with respect to x is 2y. And we can see that these things are equal, satisfying, this. So that means this is exact, which really means there exists this antiderivative that has this property. So really now, this is the claim, is that there's an antiderivative really to this exact form differential equation, which is going to be the solution to this differential equation, where this thing is its derivative with respect to x, and this thing is its derivative with respect to y. So after you prove it's exact, we can find its solution, and that's what I'll do. So what I want to do is I want to solve this exact form differential equation, and my claim is that this is the exact same equation that I wrote before, except I solved it for its first derivative, and I'm doing that because in a previous section, in differential equations, you just use the methods of solving by separable differential equations, and these things are not separables. I can't put all the x's on one side and all the y's on the other, and then integrate both sides. So there's got to be another method, and this exact form differential equation is that other method. So what I'm going to do is I'm going to rewrite this in that form. So I want I'm going to multiply this across, multiply this across, so cross multiply, and we have 2x cubed plus 2xy dy is going to be equal to negative 6x squared y plus y squared dx. And then I can put it to the other side, giving the original differential equation that we were just discussing. Now, remember that since this is exact and we prove that, we're saying that this coefficient function here, which is going to be your m of x comma y, is the derivative with respect to x of my solution. And then similarly, this coefficient function, which is we call n, is also the derivative of that solution, but the derivative with respect to y. So that's really the claim, and I'm going to kind of show that this works. So what we know is that the derivative of our solution function with respect to x is going to be equal to our m function, which is equal to this 6x squared y plus y squared. And similarly, the derivative of that solution function with respect to y is going to equal this n function, which is equal to this coefficient function, 2x cubed plus 2xy. All right, now we have choices and where to start. We tend to start with the m function and kind of work backwards. But what I need to do is I'm trying to find f, but I don't know f. I know the derivative of f. Actually, I know two derivatives of f. So we usually just start with the very first one. So since I know it's derivative, I'm trying to find the original function. So how do you get rid of this derivative? Well, we're going to integrate both sides. So what this means is that our f function, or f of x comma y, but our f function should be equal to the integral of this df dx with respect to x. So I'm going to integrate this function. So this is going to be equal to the integral of this function, this 6x squared y plus y squared, but with respect to x, because this is the derivative with respect to x. Now, integrating this with respect to x is going to give us 6x cubed over 3. Six x cubed over 3 y, because y is a constant right now, plus y is a constant, so this is going to be xy squared. Now plus some c. So plus some c. Now remember that when we're taking the integral with respect to x, that the c, just like over here, could be functions of y, that these things are constants. So really we can't say c, but we have to say that this is likely some function of y. So we're going to call this, g of y. Now simplifying this, 6 divided by 3 is equal to 2, so I don't have to rewrite that. So this would be 2x cubed. Okay. So so far this is the answer to this thing, except I haven't resolved this g of y part. But remember that this thing also has this property, that the derivative with respect to y better also be this thing. So remember, it has to satisfy both. All I've done so far is satisfy this. It also has to satisfy this. So what I'm going to do is I'm going to now take this thing's derivative with respect to y. So if I take the derivative of f with respect to y, which is, this thing, so I'm going to take the derivative with respect to y of this 2x cubed y plus xy squared plus g of y. Remember, it better match this. So this is going to be equal to, well, the derivative with respect to y, this is going to be equal to, x is a constant, so 2x cubed is a constant, so this is going to be 2x cubed. And the derivative with respect to y of this thing is going to be equal to plus 2xy. And the derivative of this thing is going to be equal to g prime of y. Now remember, these two things right here should be equal. So for these things to match, it means that g prime of y would have to be equal to 0. Also, I'm not trying to find g prime, I'm actually trying to find g of y. So what I know is that g prime of y is equal to 0. So, integrating this thing, so the integral of g prime of y with respect to y is going to be equal to, let's see, this was the derivative with respect to y. So this is going to be equal to just the integral of 0 with respect to y, and the integral of 0, in this case now finally is a constant. So finally we can write our solution. Our solution is going to be this thing, but g of y is just going to be a constant. So our f of x comma y is going to be equal to 2x cubed y plus xy squared plus c. Or sometimes they like to just write it this way. They like to say this function equal to c. So they'll just say 2x cubed y plus xy squared is equal to c. And it's kind of our choice because um c being any constant, but they're both fine. So this is going to be our solution to this particular differential equation. So let's do one more example. So I want to solve this exact form differential equation. I'm just trying to do something that has other trig function. I mean, other functions besides just polynomials. So um, you really first are supposed to show that it's exact, but I said solve the exact form, but we can kind of check. Like, let's just check the derivative of this with respect to x. So the derivative of, sorry, with respect to y. So if I take the derivative of this with respect to y, this is going to be equal to e to the x sine y. Derivative of this with respect to y is going to be equal to 2y cosine of x. And then similar, I have to take the derivative of this coefficient with respect to the other variable, which is going to be x. And just make sure that these things are the same. So derivative of this with respect to x is going to be equal to, sorry, did I do that right? This with respect to y. Yep. And then derivative of the sine is minus. There we go. Fixed it. So derivative of the cosine is minus sine. So the derivative of this with respect to x is going to be equal to minus e to the x sine y. The derivative of this with respect to x is going to be equal to 2y cosine of x. And the derivative of this with respect to x is equal to 0. So the derivative of this with respect to y is equal to the derivative of this with respect to x, which means it's an exact form differential equation, which means we can solve this using that method that we discussed, that there is an antiderivative to this. So what that means is that the derivative uh, of f with respect to x is going to be equal to this coefficient function, e to the x cosine of y plus y squared cosine of x, and the derivative of f with respect to y is going to be equal to this coefficient function, so minus e to the x sine of y plus 2y sine of x plus 2y. All right, so remember our job now is to, our solution. Remember our solution is find f. So, our solution, what we're doing is we're, finding f. Find f that has these properties. So I don't know f. I know their derivative. So in order to find f, I'm going to take the antiderivative. So we'll start here. So first the antiderivative of, this function with respect to x. So this is going to be the integral of our e to the x cosine of y plus y squared cosine of x. And this is going to be with respect to x. What I'm doing, I'm getting rid of the derivative with respect to x. So I can just isolate the function. So that's what I did. So this is going to be equal to, well, if I take its integral with respect to x, we know that this cosine function is a constant, so the integral of e to the x is just going to be equal to e to the x. So this is going to be e to the x cosine of y. And the integral of this with respect to x, well, the y is a constant, so, this is going to be y squared, but the integral of the cosine is going to be equal to the sine of x. Now, we have plus some constant. Now, remember that this is some constant, just like these y's were constant, so this is going to be some function of y. Now, remember, this is our f function. This is our f of x comma y. This is what our solution is, but it's not completely resolved. I need to know what this thing is. But we have another property. It also has to be equal to this thing. So what I'm going to do now is I'm going to take its derivative with respect to y and make sure it matches this blue function. So now, taking the derivative of this, function with respect to y, so this is going to be the derivative with respect to y of, above. So e to the x cosine y plus y squared sine x plus g of y. And what we get is the derivative of this thing. So the derivative right now, x is our constant. So the derivative of the cosine of y is going to be equal to minus sine. So this is minus e to the x sine of y. Now, the derivative of this with respect to y is going to be, remember, the sine of x is a constant, so this is 2y sine of x. And the derivative of this piece with respect to y, and we really, instead of saying g prime, it would make more sense so we know when we're integrating. This is actually, this is the derivative of g with respect to y. Or y prime is what I wrote, g prime before, but remember, we're trying to find g, and when we integrate it, we need to know what to integrate it with respect to. So if I want to find g, I'm going to have to integrate it with respect to y, because this is actually dg to dy, not just, g prime. We're working in multiple variables. So what I know is that this blue function is supposed to match this function, which means if these things match, then these two pieces right here have to be the same. They're the only spots where they differ. So then dg dy has to be equal to 2y, which means if I want to find g is going to be equal to the integral of this, dg dy with respect to y. So this is going to be equal to the integral of 2y with respect to y. And the integral of this is going to be equal to y squared. Well, 2y squared over 2 plus c, or we can say that this is just equal to, y squared plus c. So our solution function, remember our solution function is this thing right here. This is our solution. And remember this is our g function, so, these two pieces right here are the same. So finally, we can give our answer that f of x comma y is equal to e to the x cosine of y plus y squared sine of x plus y squared plus c. Or you can say it's just this thing equal to c if we'd prefer to do that. So we can say that e to the x cosine y plus y squared sine of x plus y squared is equal to c. Thanks for watching.